Hello, I'm Henri Peurasaari, also from the Haskell side of the Meetup, and today I am...
Now it's on.
Okay, thank you. Let us attempt that again. I have had plenty of experience about this, a little anecdote before we begin, as one does. As I've been filming like video interviews, and I hate those. You have to just begin and end and begin and end and begin, and you have to get it perfect because everyone else is doing that. Ugh. Anyway, now that we have the tape rolling, manipulating immutable data structures through optics. That's a lot of words. And because that is a lot of words, I will need to make sure that we all understand what we are talking about today. If you received the foreword for this, it is indeed about the thing that we all love immutable data structures because Clojure and Haskell both feature them like very prominently. But they ain't the easiest to work with all the time. So let me ensure that this is on the correct place. Good. So for types of data structures, just to make sure we're all on the same page, the mutable data structures, this is what most programmers begin with. This is the thing where you get a list, tell it to sort the list, and then you refer to the list later, the list is sorted. On the other hand, the result of the sorting is a non-type, thanks Python by the way. But indeed, when you change things in mutable stuff, it remains changed in the future. We've got the immutable structures, wonderful immutable structures that actually get completely replaced when we need a new one. And why this is done? Well, in Haskell it allows for laziness. Like you can always refer to one version, which will be explicitly that one version of it. And for Clojure, I will say that I don't fully know the design behind Clojure, but I know that you also do immutable structures, so it's probably much of the same. But yeah, the problems come in the reconstruction of the data, because accessing either is pretty much the same process, you just pick up the thing from the memory. But to change them for the other, you change the thing in the memory, and in our thing, we build the whole thing again. So, on a brighter note, this isn't as bad as it used to be in Haskell when I was writing this last time, because we now have the language extension overloaded record dot, which allows this style of access, that there's the data itself, and then there's the what accessor we want to use, so we can get the programmer out of the examples occupation here. Though, yeah, it doesn't seem to be doing much now, but we know how the structures tend to go. We like nesting structures. Nesting structures fun. You don't need to do a new structure every time. You can use the old one inside of another one. And as I mentioned, I'm not exactly a Clojure expert, but in the case of example, I think it goes a little something like this, that I can call for the occupation as it goes and associate a new occupation if need be. It seems example got tired of writing JavaScript and just changed to Twitch streaming or something. So, as I mentioned, we have the everyday struggle of wanting to put things inside other things. For the Clojurist, does this seem clear enough, or should I go over how this structure works? I'll do it anyway since nobody said anything. So, the person type is mostly the same, but there's one additional field, which is address, which is a nested data type for the address, where there's a street name, there's a house number, and there's a maybe, possibly, could be an apartment number. And I don't know how optionals are done in Clojure, and Google wasn't helping. So you'll have to do with the Haskell example only for now. And I know this doesn't actually match to nearly all the addresses in the world. That's why I'm also using string for numbers, because people are being funny like that. But for the purposes of this presentation, it'll do fine. So it doesn't get too bad yet in Haskell, since we can use the named accessors here. So we have a person, we get from them the address, and we ask for the street name from the address, and it's on null street, as example does. And we can do it optionally with the overloaded record dot going the absolute opposite way, but the way that a lot of programming is used to doing it nowadays. And Immutable you can do for get in, you can put them accessors in there and it will pick them up just fine. Though now that we have seen what is accessing things and what are nested data structures and like what's immutable, what's mutable, then we need to discuss what an optic is. Well, it's a bidirectional data accessor as per definition, which is a fancy way of saying it can get and set things. We will mostly stick to these simple samples in this presentation. We will talk about lenses and prisms, but there's more out there. We will shortly mention a few of them, but I'm not going to be focusing entirely on going over the more complex types. So a lens, the most simple one, is a data structure in itself composed of two functions. The functions being the getter and the putback. So a getter gets a value which the lens is focusing, hence the optic parallel, and the putback instead goes the other way. If we just got something, we could instead burn something onto the paper or whatnot. And for an example, if we have tuple, we can do a lens for the first value of the tuple, so that the getter is simply taking the first value, and the putback is ignoring the value in the source and putting in the new value that we as a programmer desire to put in there. Very simple. Always focuses on one thing. Always focuses on one thing. Cannot fail. That's not allowed. The prism, though. Yes?
Sorry, can I ask, what's the type of first in the previous slide? Or the type of get?
The get is of the type, here it is from AC to A, right, as a native library function in Haskell. I could have also done it with putting the A and underscore here and equals A, but I opted for the library function in this case. Though prisms. Prisms are what we use when we actually can fail on stuff. What if we don't have it? Well, there we have the embed, which is the opposite of the putback, or the equivalent rather of the putback, which creates a value out of thin air. You can use that. You can take a prism and start creating values with a prism. That's fine. Can't do that with a lens. Lens needs the input. And then there's the match, which checks if the thing you want is there. This right and left, this is all either nonsense from Haskell. Doesn't really need to be understood other than left is the fail state and right means that there's something to do over here. So here the match on just a value means something was found and it returns the a value from it. And matching nothing gives the nothing because it couldn't get anything, which works to short circuit things. Which is useful because optics are not meant to be standalone things. You're supposed to put them together. The idea goes that we make a lot of small tools, as Unix philosophy does, and then we start using them together. We start putting lenses back to back, and they form into one function or one structure with the pair of functions, as the optics are. And this process can create whole new optic types even. Should we put a lens and a prism together, the result's no longer a lens nor a prism. It becomes an affine traversal, which we cannot invoke in pretty much any other way without going through multiple hoops, and we don't want to do that anyway. So manipulation of data structures more deeply. Here we have a very nice thrice-nested tuple, as we do. And a thrice-nested tuple, well, where we need to preserve all the other values. Well, then we see we have an x that we want to put in there, and we have to write the entire data structure again. There it is, A, B, C, then x in place of D and E and F. we could do a simpler one. We could do this. Looks good to me. Like it already saves a lot of possibility for typoing something and changing things that you weren't supposed to change, which when we are restructuring more complicated data structures, there's easily the chance of just doing a simple mistake that ends up breaking the data. These are all included in Haskell's lens library, and in short, they focus on a particular element of a tuple. So we go to the second, which is BC with the DE, and then we go to the third in that tuple, which is the DE pair, and then we go to the first, which is the D, and end up setting the new value into that. We have made a little bit of use of currying so that we have left this X out, but Haskell would allow this, and natively just if you give it optic set X and the data structure, it would be able to handle it. So what of our toy data structure? Well, suppose we wanted to get the apartment so that every letter in an apartment is always in uppercase. So we take a lens for the address and a prism for the apartment because the apartment number could not be present. And by putting it to uppercase, we receive the apartment being Z0 on Null Street. We are still not too deep in this, but JSON exists. Everyone loves JSON, at least if we are to trust the amount of JSON going around the internet. Very popular in APIs. Very unstructured too. But undoubtedly, a lot of nesting going on in there. You put an array into an object, into an object, into an array, into an object, what have you. And like any popular use case, libraries exist. So there's also, in Haskell, we have a specific library with the for ASON for working with JSON, and lens ASON putting the lenses and other optics into the JSON world. And we note that it's mostly prisms out there. Can anyone tell me why we would mostly be using prisms when we are working with JSON? Well, JSON is very unstructured. We can hope a JSON conforms to a certain type, but you can never be too sure if the thing exists in that JSON file you just got. You wanted something, and you sure would be gambling if you were lensing it. Lenses cannot fail. It could break the whole program then and there. But with prisms, we survive the failure. We can go on. It short circuits into, well, I'm just not going to do nothing mode instead of I'm going to crash the entire program mode. So meanwhile, in the JSON, I have made a little bit of an example here. So it's a JSON that starts with an array of companies. We have OY Lafka AB with the CEO and some employees, and the second street auto repairs, much of the same, doesn't fit on the screen, but you get the idea. And now we are going to start digging in. So here we can see that, okay, so the nesting has started happening. This is with the helpers from lens ASON. Key for companies. Yes, this is an object with companies in it as a key. Then in the next one, then we have this is supposedly going to be an object, but I've typoed it. Oh well. So OY Lafka AB specifically. We are getting the employees from OY Lafka AB. The nth employee, which is 0th, the first one, their occupation, asking it kind of to give us a string for it from the sample JSON, and we get, there's a programmer in there. That's a programmer what you just asked for. Well, we can change things too. And this is a little bit more complex since we are using over, which gets the values, applies a function to them, puts them back in, and serializes it all back. So for companies, all of the companies, all of the employees of the companies get the occupation string, and we capitalize it by putting the first letters in each of them as capital case so that everything looks neat. We have a programmer with a big P and pro gamer with 2 capital letters and what have you. For some reason, I couldn't fit the results on this, so you'll just have to take my word for it. And, well, we can do more. We can get indexed things out of this. Like, if we wanted to get all of the employee names with the employers who's employing them as knowledge we wanted to have, we could do ask for the companies, use that as the index. So usually the indexing is like right dominant, so it would just give them numbers that this is the 0th employee, this is the 1st employee, this is the 3rd employee, and then for the next company again, this is the 0th, this is this, this is that. But since we are going left associative, it puts the company name in there. So we'll get that information. And we get a neat list of all of the people that are employed by all of the companies and know what companies they are employed in. So this has been an introduction to the concept of optics, how they exist. And I could show a lot more things about them, but at that point it becomes perhaps indigestible for someone who's not seen them before. But in case someone's interested in further reading from this primer, for using Haskell, Chris Penner has written a most commendable optics by example. And if you want theory, the Lens Library repository wiki has pretty good past or you could look at my bachelor's thesis if you can read Finnish. Why not? I did that. And then there's the special thanks for the Creative Commons licensing for the images I had in this talk. Now, I have left time for questions because this is kind of a crash course. So, is there anything about the optics that you people would like to discuss further right now? Yes?
Are there good optics implementations outside Haskell?
I looked for implementations in Clojure, and there was this Spectacle library, but it was considered to be very early alpha, and that was 4 years ago, so your mileage may vary. But of course, Google's pretty bad these days, so it's hard to tell.
There's something called Spectre, which is not optics in this way, but another approach. Has many of the same features. You can also do like nested traversals and stuff like that. So that's maybe something to have a look at. It's not based on like the theory of optics, but similar use case.
Haskell also has an alternative library to Lens, which is called Optics, and I haven't used it. It's been made and it's being maintained by a reputable consultancy, Well-Typed. But since I already know the syntax over on the Lens side of things, it's difficult for me to talk about it further.
There are lenses also in JavaScript. In Clojure, actually, there is also this meander, which is
meander is kind of like that.
Similar functionality.
Yeah.
And also there is the concept of a generic lens, so that we don't need to specifically write everything down, but we can, if our data types support generics, we may use them to infer that, okay, there could be a lens for this field. And we are able to also store a combined optic as a variable if we use that a lot, so we save some time ourselves writing them down each time.
maybe one of the benefits of optics and lenses are that they are composable, but their implementation is a bit difficult. If you, for example, unfortunately you didn't show, but one Verhoeven lens is, the type of them is pretty much undecipherable unless you're a Haskell expert.
Yes, I wrote my bachelor's thesis with Van Laarhoven lenses and then looked at them for this presentation and went, nobody's going to get this.
Just a comment, I recommend it as an exercise proving the equivalence between this Van Laarhoven and direct lens representation, because that really you grok the concept once you manage to do it. The other direction is a bit more difficult.
But that's also maybe one of the reasons why you rarely see lenses or optics in other languages, because it does the implementation is really difficult to understand, and the types really help there to keep things in track, and composability with the one lenses with the normal function composition and trying to simulate that with, I don't know, Clojure or JavaScript. That sounds like an exercise in feasibility.
Yes, like there's something I could note about Clojure that how far back must I go? I had it, yeah, here. This get in and assoc in and what have you. This syntax is very reminiscent of like the optic paradigm already. And I should note that it's mostly like that it's presented in the spectacle library. So maybe it was adopted as this kind of syntax for the language as a whole instead than resuming on as a separate project. But again, I have no real intimate knowledge about Clojure, so it's hard to say if that's the case or if it just looks like it.
Maybe, well, this is a good place to ask, because I think that this get in is implemented with recursion, or is it not? I don't know. But it's doing this kind of recursive traversal over some list of tokens or a path. I think that kind of approach is easier to adopt to wider range of languages, because I think that Haskell optics, they kind of leverage Haskell specific optimizations and representations of the language, because it seems to me that lenses in these languages like Elm and Kotlin, they are quite cumbersome, and I'm not sure if they are very optimal, because I think that for instance, if you have these direct lenses, then unless your language is very cleverly designed, you get a bunch of nested records. If you compose multiple lenses together, you get a nested record, which is not nice. But I think that Haskell can optimize these lenses better.
Yeah, like for our solutions, what we've been using in the lens library sense and the Van Laarhoven function encoding, it allows them to be just composed functions together. They are not composed structures, which would cause the greater overhead cost to it. But when we have functions that we can put together that form one structure or a function that emulates that structure, that does help us along a good way in not burning our performance on the altar of looking nice.
It's probably been nearly a decade since I last did it, but I remember back in my more junior days I was working with Clojure a little bit on one project where I was modifying a whole JSON structure at once, which is, now I'm thinking that it's really reminiscent of what you would do with lenses, with traversals. But I used something like tree traverse or something like that in Clojure, and to be honest, I haven't seen as ergonomic solution in Haskell yet even. That's
Yeah, like officially, of course, it is more recommended to deserialize the JSON into like actual data structures within the language that one wants to use. But for some operations, and especially if we don't know if the JSON is going to be well behaved, or if it's going to be a gunslinger from the Wild West ready to shoot holes into our beautiful program, that's when we take out the ASON lenses, just to like ensure that even if the JSON's been malformed in some way, the worst that can happen is that we cannot work on it.
I would like to encourage people to try out lenses if you haven't, since I wrote some toy lens library in Java and I have used it even in production. But I only wrote like lenses and then got bored, so there's no traversals or anything, but that's just lenses. But I have found them still quite useful because I happen to work in API stuff, which in some cases I'd like to change some random values deep inside the structures, and I like to keep everything immutable. And I don't really mind even if Java is quite a horrible language and the type system lacks, but I can still like live with the lenses even if it's not that nice as in Haskell. But it does help me. I don't like to turn into mutable, and I don't like to write by hand all these alternative constructors or whatever to rebuild the stuff. That just seems to work nice.
Lenses also have support in template Haskell, but I don't do template Haskell, so I can't talk too much about it. The Optics by Example book does extensive use of template Haskell things, but well, one can learn more about it that way. I wanted to say here that, of course, because this is affecting multiple things, this can't be a lens, a prism, nor an affine traversal. This incorporates the ideas of a fold in itself, and it is an actual traversal, which means that since it is a traversal, we could use it to do some kind of effects in addition to just getting or like changing data. We could do that, okay, so we have these job titles. What if we store them into an outside file? Well, we could do that as part of traversal. We change the capitalize into something else. The functions allow for it. And one of the examples that was, well, Kubernetes configuration. A lot of JSON goes around there. Do you want to do changes in Kubernetes? Well, you could do it by Optics. If it doesn't have what you expected, nothing changes. If it does have what you expected, well, you get your changes. Ain't that great? Double all of the memory allocation at once. Why not? Good times. Don't believe there were any other thoughts on the matter at this time. Seems the crowd is satisfied. Thank you.
Thanks, Henry. So I guess I don't know how long the break will take, but we'll take a break in minutes.
Osin, jossa yritetään käyttää sitä arrow-kirjasta.